In this video, we're going to continue our discussion of natural deduction for propositional logic. And in particular, we're going to look at the rules for negation and disjunction. Now, these rules are more confusing and complicated than the rules in the previous video. And I want to stress, as I always have with symbolic logic, that the only way to grasp this stuff is to practice, practice, practice. So doing practice problems will help you to see how these rules apply, that is, how they can be used to derive things. And through seeing how they can be used, that is how you'll come to grasp how they make any sense. So if you're left at the end of this video feeling like these rules don't make any sense, you're in good company. That's not a problem. It's a very natural reaction. The way to solve that is to do a whole lot of practice problems. The rule for introducing disjunction is very, very simple. Maybe the simplest one of all. So if you have phi on any line, then on a new line you can write phi or psi. That's all. That's all there is to it. And notice psi can be any arbitrary formula. The reasoning behind this is, well, look, if you know phi is true, then what does it mean for a disjunction to be true? Well, it means at least one of these is true. Now, you already know one of these is true. So once you have phi, you can disjoin it with any old thing, no matter whether it's true or not, because you have one of the disjuncts being true, and that's all that's required for a disjunction to be true. Here's an example of that and how it could be useful. Suppose you start with P and P or Q implies R, and you want to get to R. Well, that's very easy. You already have P, and so you can disjoin it with any old thing, which means on line 3 we can write P or Q. And that's what we needed in order to use arrow elimination on line 4 to get R. So remember, back to arrow elimination, if you have the antecedent of a conditional, then you can write the consequent of the conditional on a new line. So a very powerful tool there we have in the disjunction introduction. The rule for disjunction elimination is a little bit more complex, but the idea here is you want to ask yourself, if I already have a disjunction, how can I apply this to drawing a new conclusion, Kasi? Well, the way to do this is to show that both of the disjuncts, phi and psi, lead to Kasi. So to eliminate a disjunction, we need two arrow statements. We need an arrow statement with each of the disjuncts in the antecedent position, and both of them pointing towards the very same consequent. So again, the idea here is, what if I want to prove Kasi, and I'm working with a line that already has a disjunction? Well, I need to produce two arrow statements, just like this, each one pointing to Kasi. So the idea here is Kasi follows from phi or psi, just in case Kasi can be derived from both phi and psi. Here's an example. Suppose ultimately what we want to get to is R, and we start with a disjunction like this, P and R or Q and R. Like always, we're going to start by listing our premises as assumptions. So that's what we've done here. In this case, we only have one premise, so we start with just one assumption. Now, the next thing we need to do is produce two arrow statements. So how are we going to do that? Well, we need to think back to last video where we had the arrow introduction rule. And how did we introduce arrows? We used the introduction of the arrow rule, How do you use the introduction of the arrow rule? Well, you need to make some additional assumptions and then derive the arrow statement from there. So think back to the previous video. We know that we want to derive some arrow statements. The first arrow statement needs to have the first disjunct in the antecedent position. So we're going to assume the first disjunct and then show that we can produce an arrow statement with R in the consequent, because that's what we're ultimately going after. So that's easy enough. Once we have P and R, we can use our AND elimination rule to produce R, right? If P and R is true, well then R is true. So that's simple enough. Now that allows us to use our arrow introduction rule. We've shown that if we assume P and R follows. So we have the very first arrow statement we needed. And remember, that's just what we were going after. We need to show each of the disjuncts leads to what we're trying to derive. So we've accomplished the first part of our task. But remember, to use disjunction elimination, we need two arrow statements. So we need to produce another arrow statement. In particular, we need to produce the statement that Q and R arrows R. So how do we produce that? Well, we are going to just assume Q and R and show that R follows from it. So we introduce a new assumption. And from that, it's easy enough to derive R through a simple conjunction elimination on line 5. We just freed up R from its binding in this conjunction and wrote R on line 6. Well, that's what we needed. We've shown that if we assume Q and R, then R follows. So we can write our arrow statement. Q and R implies R using arrow introduction on lines 5 through 6. Remember, just like above, we draw our dotted box around these to show that we just introduced an assumption for the sake of introducing an arrow. We're never going to appeal to these again. That was just saying, suppose this is true, then this follows. We don't actually know whether this is true, but that doesn't matter because we're just trying to get this hypothetical statement down here. Well, if we look at this, now we've got just what we need. We have shown that the first disjunct leads to R. We've shown that the second disjunct leads to R. So we can apply our elimination of disjunction rule on lines 1, 4, and 7. And we can just write R all by itself. And that's exactly what we wanted to prove, so we're done.